The first image appeared only a few hours earlier, and the moment it reached the astronomy community, it triggered immediate reaction across every forum and research channel. Captured by Mitsunori Tsumura on November 22, 2025, the frame showed the interstellar object 3I Atlas, positioned near the galaxy NGC 4454. At first glance, it looked like a standard comet, a bright core and a trailing tail. But as astronomers examined the image, the familiar shape began to break down. Something was off. Not slightly, not ambiguously, but completely. The object looked like a comet refusing to follow comet physics. The tail was the first anomaly that grabbed the eye. Instead of broadening with distance like dust blown from an outgassing nucleus, it held steady in a tight, pencil-straight beam stretching millions of kilometers across space. Typical comets produce tails that diffuse and widen. Sunlight and the solar wind pull particles into a gentle fan. But 3I Atlas presented a stubborn line, thin, collimated, unnaturally rigid. It wasn't curved, bent, or distorted in the slightest. It did not respond to orbital motion the way dust or ionized particles should. In Tsumura's image, the tail looked more like a laser stroke on the canvas of space than the soft plume of an evaporating ice ball. The structure showed no striations, no clumps, no embedded brightness variations, none of the usual turbulence that natural cometary jets imprint onto their outflow. It was as if whatever material or energy Atlas was pushing out had been compressed into a geometrically perfect filament. The second element breaking expectations was the coma, the luminous envelope around the nucleus. Most comets, even those that appear roundish at a distance, reveal asymmetries upon closer inspection. Jets erupt from specific vents on the nucleus. Dust condenses in uneven shells. The inner coma shows clumps and spirals depending on rotation and internal structure. But Atlas, in this exposure, looked eerily smooth. The coma was nearly perfectly spherical, its brightness transitioning outward with unusual uniformity. If one removed the tail entirely, the core looked like the kind of mathematically idealized glow artists use to depict a point source. Real comets are messy, uneven, and turbulent. This one resembled a symmetric, controlled emission. And in the very center, the nucleus region was not fuzzy or smeared. It was tight, compact, almost star-like, as if the internal condensation was being restricted to a pinpoint rather than dissolving into a cloud of ice particles. Then there was the faintest but most provocative detail of all, a secondary filament. Running nearly parallel to the primary tail, this second structure was subtle but undeniably linear. Normal comets often form two tails, dust and ion, splitting at visible angles. But Atlas's secondary feature sat too close to the primary, diverging by too small an angle to qualify as a standard dual-tail system. It looked like a second beam, a whisper of something flowing in the same improbable direction. Few observers even caught it at first, but those who did recognized that this alignment was not a trivial artifact. It pointed to a process operating with precision, not the chaotic spew of natural outgassing. Within hours of Tsumura's image circulating, additional confirmations began streaming in. Across continents, entirely different amateur astronomers had captured the same anomalies using their own telescopes. On November 23rd, astronomer Peter Collins obtained an image with a 0.2-meter reflector, showing a distinct anti-tail, a narrow sunward jet pushing directly toward the sun. Dust particles typically fall behind a comet, not forward. A sunward spike requires an unusual geometry, and even then, it normally appears as a broad fan rather than a dagger-like ray. Collins' photograph revealed a thread-like anti-tail stretching perhaps 1 million kilometers. It was faint, but structurally consistent with Tsumura's image, and hinted that the strange directional behavior wasn't a one-off glitch. One day later, on November 24th, another observer, Patrick Goffin, provided further verification. Using a 0.2-meter setup, Goffin recorded a refined view of the antitail, its narrowness and symmetry echoing the features seen before. He noted that the tail's extension remained sharp even under different exposure stacks, which meant it wasn't merely a processing artifact. Meanwhile, at the Markarian Observatory in Armenia, a 0.35-meter telescope added a fourth data point. Again, the same tight primary tail, the same oddly spherical coma, and a faint antitail aligned along the same vector. Although the image showed slight elongation from motion or stacking, the core morphology stood out unmistakably. Over 72 hours, 3 independent observers at 3 distinct locations documented an interstellar object that defied normal comet physics on multiple fronts. These observations quickly drew the attention of Harvard's Avi Loeb, who published an analysis arguing that the morphology of 3I Atlas could not be explained by conventional sublimation-driven dynamics. His argument centered on the physical implications of the massive tail and antitail seen in the amateur images. According to their projected lengths, approximately 5 million kilometers for the main tail and 1 million kilometer for the antitail, the ram pressure acting on the comet would have to exceed the solar wind pressure at that distance. In order for standard sublimation to produce such extended collimated features, the comet would need to expel matter at staggering rates, shedding billions of tons of mass within a couple of months. But losing that much material is incompatible with the survival of the nucleus. Loeb notes that if 3I Atlas were an icy object of the expected size, roughly half a kilometer in diameter, based on brightness and albedo estimates, losing billions of tons would correspond to around 10% of its total mass. No comet can sustain that level of erosion without disintegrating, fragmenting, or showing large-scale structural instability. Yet Atlas seemed not only intact, but producing a tail more stable and orderly than those of ordinary comets. Loeb further compared these morphological observations with the orbital tracking data from JPL horizons. Near perihelion, astronomers recorded a non-gravitational acceleration, movement that deviated from purely gravitational influence. Typically, this kind of acceleration comes from microjets of sublimating gas pushing the nucleus, like microrockets. But in this case, the direction and magnitude of the acceleration did not match what standard sublimation models predicted. For a comet with Atlas's alleged mass, the observed acceleration would require mass loss rates even higher than those implied by the tail dimensions. Again, the math failed to align. The comet was moving as if it were being pushed, but the amount of natural thrust required was self-destructive. This discrepancy led Loeb to raise a provocative alternative. Perhaps the acceleration was not the result of low-velocity gas sublimation, but of a small amount of high-velocity exhaust, something more akin to a jet or thruster. In that scenario, the object would not need to shed billions of tons. It could achieve the same momentum change by expelling far less mass at far greater speeds. It was a suggestion rooted not in speculation for its own sake, but in the same physics that governs spacecraft propulsion. High-velocity exhaust moves craft efficiently with minimal mass loss. If 3I Atlas were emitting a tightly controlled ionized plume along a vector, the resulting morphology would look suspiciously like what the images revealed: a clean, collimated tail, unwavering direction, and coherent structure even across multiple days and multiple telescope systems. But not everyone accepted the artificial propulsion hypothesis. Many astronomers pointed out that 3I Atlas is an interstellar object with an unknown composition, possibly containing volatile species rarely seen in solar system comets. Some argued that a CO2-dominated coma, which 3I Atlas appears to have based on infrared spectroscopy, could behave differently under solar wind interactions. Others noted that projection effects can create illusions of perfect symmetry when viewing geometry aligns just right, and that ion tails can behave in unusually linear ways when the magnetic field surrounding the comet stabilizes temporarily. Nature is capable of producing strange outcomes, especially when dealing with visitors that originated beyond the sun's domain. Still, the consistency across multiple independent observers gave weight to the idea that 3I Atlas was not simply exhibiting a quirk of viewing angle. The secondary filament, the star-like nucleus, the perfect coma, and the dual beams had now been documented under varying conditions and equipment. More intriguingly, this was not the first time Atlas had broken expectations. Earlier in the year, polarimetric measurements revealed a deep negative polarization branch, something unprecedented in cometary science. Pre-perihelion imaging had shown asymmetric outgassing patterns that did not match predictions. Even before reaching the inner solar system, Atlas had been a rule breaker. Now, with its bizarre double tail structure and implications of impossible mass loss, it seemed to be repeating the pattern. Every instrument pointed at 3I Atlas produced more questions. Every new observation made the object harder to classify. And the most significant observations were still ahead. On December 19th, the comet would make a relatively close approach, giving the world's largest telescopes, both ground-based giants and space observatories like JWST and Hubble, a chance to capture high-resolution data unlike anything yet obtained. If the comet's nucleus was fragmenting, rotating, or jetting in unexpected ways, those images would reveal it. If its behavior could still be reconciled with natural physics, that would become clear as well. Conversely, if its acceleration and morphology pointed to something more exotic, the scientific world would face a very different kind of conversation. For now, 3I Atlas remains a mystery suspended in the darkness between planets, an interstellar wanderer bearing patterns that do not fit the templates of ordinary comets. Amateurs with backyard telescopes have captured images that confound astrophysicists, while seasoned scientists debate whether the object is simply a natural oddity or a sign of something unprecedented. What is certain is that 3I Atlas has broken the rules before, and in these latest images, it has done so again, more dramatically than ever. Whether nature is surprising us or something more deliberate is at play, the final answer waits in the data still to come. Until then, 3I Atlas stands as one of the most intriguing and perplexing objects ever witnessed entering our solar system.